Hello. In this recording, I like to cover the proof of Fermat Theorem. Even though we did it in class, but I thought it would be good that we have it in record that where we note the proof. The proof actually is not difficult. It's just it helps us to understand the concept we learned before. Okay, so first let's look at the statement in Fermat Theorem. So if f, okay, of course, f is a function, has a local maximum at C. Okay. And if f is differentiable at C, so the derivative of the function at C exists. Then the derivative of the function at C must be zero. Must be zero. Okay. So to prove this theorem, and of course we're gonna use the definition. We're gonna use the definition of derivative exists as a point. Okay. So we know that, well, so first of all, we have two conditions. F has local maximum at C or local minimum. Okay, it could be local minimum. Local minimum. So in the class, we proved that we assume that if it has local maximum. So now in this lesson, I will prove, I will assume that f has the local minimum. Okay, so we assume that f has local minimum at C. What does that mean? By definition, it means that f of C is a local minimum, so that it is smaller than or equal to every other number in the neighborhood. So C plus H, and H is a positive. Well, H is just, it could be positive, it could be negative. Okay, it could be just any number. So C plus H is in the neighborhood. Okay, so with this is some for any H. Okay, for any H, that is sufficiently close to zero. So in the neighborhood, so C may be positive, maybe negative, but because f has local minimum at C, so f of C is less than or equal to C plus H, where H is sufficiently close to zero. So in a small neighborhood of C, okay, by definition. So with that, we know that f of C subtracted from f of C plus H. Okay, f of C plus H, subtracting f of C, that's going to be greater than or equal to zero, right? Because f of C is the smallest. That for any H, that's sufficiently close to zero. Now, by definition, and by the definition of limit, hold on, I'm going to bring the definition of limit. So limit as H approaching zero, definition of derivative, which is c plus h minus f of c divided by h. And of course, this limit exists because we were told so, right? So the derivative of the function as c is that limit, okay? And we know that this exists, right? And what is more, and you can see the numerator is always positive or zero, but h approaching zero could be approaching zero from either side, right? So this limit, if we take a limit as h approaching zero from smaller than, and then this limit is going to be, because the numerator is positive or zero, the denominator is negative, so positive divided by negative is going to be less than or equal to zero. Okay, and the same limit, right? If I push zero from larger than zero, this time h is positive, the numerator is positive or zero, so this limit is going to be greater than or equal to zero. And both must be true because this limit exists. So I'm quoting this theorem. Okay, the theorem says if limit of certain function exists, actually, let me bring back the flashcards. Okay, the flashcards on limit exist at a point, okay, which is right here. Going to bring that limit. Hold on. So that limit exists, and the limit from left and limit from right both exist, and they are the same number. Okay, so I'm going to bring that back to you. Okay, so right there. So this is the theorem from the flashcards that we are very familiar with, right? So it is this limit we are referring to. Okay, so derivative of function as c is less than or equal to zero and greater than or equal to zero. So then the derivative of the function as c must be zero because both must be satisfied. And that's it. That's the end of the proof. End of proof. But what's the use of this theorem, right? We're going to talk about the use of theorem because what does this theorem tell us, right? The theorem tells us, what does the Fermat theorem tell us? Right? The Fermat theorem required two conditions, right? F has local max or local min. It's local max or local min. Has a local max or local min. Has a local max or local min. And secondly, the derivative exists. Derivative exists. Then that's if, right? If A, then B. Then the derivative of the function as c must be zero. Yeah, so this is the if f has a local maximum or local minimum and the derivative exists, then the derivative at the point is 0, right? So if A, according to that principle we learned, right, the logic principle, if A, then B, right? If A, then B. So this is if, right? If, and this is A, then B. Okay, if A then B is true, then we can say if not B, then not A. Okay, not B, then not A. Then what does it mean in this case? Right? So if right, if the derivative is not 0 at a point C, which is the opposite, right? If not A, if this is not equal to 0, then, and of course here we already assume the derivative exists, then f has no local max or local min. Okay, so from the reading of the Fermat theorem, and we need to understand that. So if the function has a derivative as, at a point, but it's not as equal to 0, then f has no max or local min. And this also gave us the reason, right? Because even though Fermat theorem did not tell us, right? And does not tell us where we can find the local max, local min, but it tell us how to find the candidates where we can find the local max, local min, which is the derivative must be 0. Derivative must be 0 in order to find local max, local min. And as a result, we understand the critical number definition. So what are called critical numbers, right? So critical numbers are defined as a function. First of all, a critical number, we give it a name. Okay, critical number, we give it a name C. Then C must be in the domain. So number 1, C must be in the domain. C is in the domain of the function. Okay. Secondly, that the derivative of the function as C, the derivative of the function as C must be 0. Or f of derivative of the function as C does not exist. Does not exist. Okay, so satisfying these two conditions, right? So C must be in the domain. And secondly, either is equal to 0 or it is not differentiable at that point. And these are the critical numbers. So critical numbers basically tell us how to find, give us the candidates of local max or local min. Okay, so when we study the extreme value theorem, which says, right, there's an extreme value theorem. Okay, I'm gonna bring the extreme value theorem. Let me bring that to you. Where's our extreme value theorem? The extreme value theorem is very, very important theorem. it tells us that if a function is continuous on a closed interval, okay? So if we have a continuous function on a closed interval, then f attains absolute max and absolute min in that interval. Okay, and combined with the critical number idea, and of course, as a result of Fermat Theorem, we have a critical number idea. Then we have the following steps: how to find absolute max, absolute min. Okay, so I'm going to bring that to you as we're going to do an example. How do we find absolute max, absolute min? On a closed interval, if the function is continuous. Okay, so combined with all of these information, right, all these theorems, we have closed interval method. Closed interval method, right? And this closed interval method, the first step basically says we find all the critical numbers in the interval, open interval, and then find the values of the function at the critical numbers, and then find the values of function at endpoints, and then you just compare these numbers, whichever give us the largest function value, and that's the absolute max. And likewise, whichever one give us the smallest value, and that will be the absolute min. Okay, so now we have all of these theories that we need. We have the concept. Let's look at a homework question from last week. I think this should be from, well, let's just look at a homework question. Okay, let's just look at a homework question. Hold on. So I'll show you the homework questions. The homework questions I refer to would be the let me put a share screen right here. Okay, so we're gonna pick a question, and we did some questions in the classroom. So let's look at number 39. Okay, let's look at number 39. This is just to find the critical number. This is just to find the critical number. Okay, so we're going to copy the question. We're going to copy the question. I'm going to reshare the screen. Okay, so just to find the critical numbers. They're pretty plural because we don't know how many to expect. And 39, and we have a capital F. F of x is equal to x raised to the power of 4/5 and multiply x minus 4 to the power of 2. Okay, so that's to find the critical numbers. So we don't have a closed interval here. We just find the critical numbers. So what are the definitions of critical numbers? We know the definition of critical numbers, which is right here. So I'm gonna bring it up for our reference. Okay, so critical numbers. So in order to find critical numbers, we know that first of all, the critical number must be in the domain of the function. Let's see, what's the domain of this function? The domain of this function is, we take the fifth root, right? Obviously, the domain is all real numbers. All real numbers. All real numbers. And then we're going to start taking derivative. Capital F. And we're going to use product rule. When we use product rule, this is F, and the other one is G. So F prime right? So that's going to be 4/5 x raised to the power of 4/5 minus 1. Multiply the square of x minus 4 unchanged, and plus the next one is x raised to the power x raised to the power 4/5 multiply the derivative of x minus 4 squared. That's going to give us 2 times x minus 4. All right. And then we're going to find critical numbers. Critical numbers, by definition, that we need to set a derivative equal to 0, or where the derivative does not exist. Okay, so let's organize the function so we can so here we can see better. Okay, 4/5 minus 1, that's 1 is 5 under 5, so that's going to give us negative 1/5. Okay, negative 1/5. So we're going to simplify this function. How do we simplify this function? It looks like we can factor out x minus 4. Okay, we can factor out x minus 4. And we can also factor out x raised to the power of a negative 1/5. Okay, we can factor out this piece. But this piece we don't have, right? We have, if we have x to the power negative 5th, and we have to multiply x raised to the power of positive 1/5, right? So this piece is factored out. This piece is factored out along with that, right? So this piece is out, right? We put it over here, and these pieces are out. So this will make x raised to the power of what? 1, right? So plus x multiply, we're factoring them out, sorry. We're factoring them out. Let's see how I do it so you can understand. Hold on. So I'm not going to take it out, okay? So x raised to the power negative 5th, this is a 4/5, right? And over here, there's x to the power x minus 4. Now I'm just putting things, and then we have a 4/5, right? We have a 4/5. We just keep everything together. We're not factoring anything yet, okay? So 4/5 from here, x raised to the power negative 1/5, right? And x minus 4 squared, x minus 4 times x minus 4. So we're good. Nothing's changed. And here on this side, I'm having them organized in such a way that I'm going to put the 2 in front of it. Okay, so now you can see clearly that we're going to factor this piece out. Okay, we're going to factor that piece out. We're going to factor this piece out. Okay, so that piece identically, they're being factored out. What else can be factored out? How about numbers? How about numbers? Do we want to factor out 1/5? Sure, we can. Let's keep it that way. Let's keep it that way, okay? We would do later. We do later, okay? So now we're going to factor out the box part, right? That box part is factored out. So what do we have left? We have 4/5 times x minus, so 4/5 times x minus 4, right? On the second part, we have 2 times, right? So here is already x, right? It's x, so it's just 2 times x. Simplified. So if you want to double check, you can go ahead, double check and pause the video, right? So these are basic algebraic skills. Okay, so that part is factored out. And we can organize the term inside, right? So now I can remove the box. Oops. We can remove the box. I can remove the box. X to the power 1/5 can be written as 1/5th root of x. So that's in the denominator. We know x cannot be 0. For the domain of the derivative, x minus 4 stay here. Okay, we can put it up here. And the question is, we're going to organize that term too, right? So 4/5 times x, that's going to be 4/5 times x minus 16/5 plus 2x. Okay. And the rest just simplify. Combine like terms. 4/5, 2x. 2x is, if we use 5 as a common denominator, we have 10, right? So the same denominator, so that's going to be 14, right? Minus 16/5. So when we set it equal to 0, so let me write it this way, which doesn't change anything, right? So you can write it this way. So now we're really looking for numbers such that the derivative is 0, right? So we're going to set the derivative equals to 0. When we set the derivative equal to 0, right? Denominator certainly cannot be 0. And be aware, the domain of the derivative, right? The domain of the derivative is x cannot be 0. X cannot be 0. And at that point, at 0, the derivative is undefined. Okay, so that makes 0 a critical number, right? That makes 0 a critical number, according to the definition of critical number. And we have two other numbers that can be solved from when we set the derivative equal to 0, denominator cannot be 0, so the numerator must be 0. And using zero product property, hold on, I dropped the parentheses by accident, right? So we have x minus 4 equals 0, or the parentheses, and that is equals to 0. First, it's easy to solve, x equals to 4. And the other one, you just have to be patient to solve it. And you're getting x, right? We're getting another number, right? So we have 14/5 times x equals to 16/5. 16/5. Right? And then we multiply both sides by the reciprocal of 14/5. That's 5/14. So 5/14 multiplies 16/5. So eventually we get x equals to, that's 16/14. 16/14 reduced by 2, that's going to be 8/7. Okay, so finally, the critical numbers are, we have 3 critical numbers. One is 0, right? C equals to 0. C equals to 4. And another one is C equals to 8/7. You can use the symbol C. You can also use X. As long as you indicate these are critical numbers, then you are fine, right? All right, so next example, we like to work out a example that, on the closed interval, we go through all these steps. Okay, the question I'm going to choose is going to be f of x. This is on your homework as well, okay? So this is going to be the question that is f of x. Okay, this is example number 2 now. Okay, the previous one was example number 1, right? So example 1. right? Example 1, find all the critical numbers. You know how to do that. Example number 2, we're going to do the following. We're going to find, wait a second. This should be the homework question. Hold on. Okay, I'm going to choose a homework question. Yes. Hold on. I'm going to choose a homework question so we can apply. Just 1 second. Okay, I'm getting there. I'm getting there. Okay, I think we found it. Okay. We want to find the absolute max and the min in the closed interval given in a given closed interval. Okay, so this function I will be of our choice. I'm going to choose this question. This is f of x equals to 1 minus, wait. Let me choose this logarithm function. So f of x equals to ln x. And the interval of our consideration is, well, in fact, it is not a closed interval. It is not even a closed interval, so that we actually cannot apply extreme value theorem, but we can still try to find the local max, local min, because we know this function, right? It just said some of them may not exist. Okay, we understand ln x, so this cannot be applied entirely. Okay, this closed interval method cannot be applied entirely because we don't have a closed interval. And now what we can do is that we can still find critical numbers. Okay, so critical numbers. Okay, so how do we find critical numbers? We're going to take a derivative. Okay, the derivative of ln x is 1 over x. Oops, 1 over x, right? And we set it equal to 0. We set the derivative equal to 0. What do we get? We set it equal to 0. No solution. No solution. Okay. This derivative, 1 over x, the domain is also, the domain is x must be greater than 0, because you can only take a derivative for x is larger than 0, right? The domain of ln x is x must be larger than 0. Only for x larger than 0, you can take a derivative. So after we find the derivative, then it's 1 over x. So the domain is still the domain of the derivative is also x greater than 0. Is also x greater than 0. We have no critical value. However, there's no critical numbers. no critical numbers. Okay, so can we find the max or min? Let's try. Okay, if we look at the functions graph, right, and we know that because we have a one end of the interval is closed, right? So from 0 to 2, right? So let me make a little adjustment to the picture. And the view is from right, so this curve. And because at a 2, right, the end point, which is 2 ln 2, I put this dot, okay, as an increasing function, it has an absolute maximum. There's absolute maximum, but it doesn't have minimum. It does not have minimum, okay? So absolute max is f of 2. Oops. F of 2, which is ln 2, right? No absolute minimum. This question did not ask for local max, local min, right? And there are no other local max, local min, okay? But it's not asking for it. So this is the basic review for primarily for Fermat Theorem and its application. We are going to apply these ideas for the future questions, which is coming up soon. Thank you for watching.